Hello students, this is Usha from G.K.Jain High Secondary School. Today we are going to see the 12th standard physics current electricity part 3. In this we are going to discuss about the applications of Ohm's law, that is Kirchhoff's law. Let us move on to the topic. 12th standard physics current electricity part 3. Electric cells and batteries. An electric cell converts chemical energy into electrical energy to produce electricity. It contains two electrodes immersed in an electrolyte. It is shown in the diagram. Several electric cells connect together form a battery. When a cell or battery is connected to the circuit, electrons flow from the negative terminal to the positive terminal through the circuit. By using chemical reaction, a battery produces potential difference across its terminals. This potential difference provides the energy to move the electron through the circuit. Here the diagram shows the commercial available electric cells and batteries. Electromotive force and internal resistance. A battery or cell is called a source of electromotive force, simply EMF. The term electromotive force is a misnomer since it does not really refer to a force but describes a potential difference in volt. The EMF of a battery or cell is the voltage provided by the battery when no current flows in the external circuit. Electromotive force determines the amount of work a battery or cell does to move a certain amount of charge around the circuit. It is denoted by the symbol XI. It is pronounced as XI. An ideal battery has zero internal resistance and the potential difference across the battery equal to its EMF. But a real battery is made up of electrodes and electrolytes. There is resistance to the flow of charges within the battery. This resistance is called internal resistance R. For a real battery, the terminal voltage is not equal to the EMF of the battery. A freshly prepared cell has zero internal resistance and it is increasing with aging. Determination of internal resistance. Here shows the diagram. The EMF of the cell Xi is measured by connecting a high resistance voltmeter across it without connecting the external resistance R. Since the voltmeter draws very little current for deflection, the current may be considered as open. The circuit may be considered as open. Hence, the voltmeter reading gives the EMF of the cell. Thus, external resistance R is included in the circuit and the current I is passed through the circuit. The potential difference R is equal to the potential difference across the cells V. So, the potential drop across the resistance R is V is equal to IR. This is named as first equation. Due to internal resistance R of the cell, the voltmeter read a value V which is less than the EMF of the cell Xi. This is because certain amount of voltage IR has dropped across the internal resistance R. Then V is equal to Xi minus IR. So IR is equal to Xi minus V. Name it as second equation. Dividing equation 2 by 1, we get IR divided by IR is equal to Xi minus V divided by V. So R is equal to Xi minus V divided by V into R. Since Xi, V or R are known, the internal resistance R can be calculated. Cells in series. Several cells can be connected to form a battery. In series connection, the negative terminal of the one cell is connected to the positive terminal of the second cell. The negative terminal of the second cell is connected to the positive terminal of the third cell and so on. The free positive terminal of the first cell and the free negative terminal of the last cell become the terminal of the battery. Suppose n cells each of EMF Xi volt and internal resistance R ohms are connected in series with an external resistance R. Then the total EMF of the battery is equal to n Xi. The total resistance of the circuit is equal to NR plus capital R. By Ohm's law, the current in the circuit I is equal to total EMF divided by total resistance. N Xi divided by NR plus R. Now we'll see the cases. Case A, if R is very much lesser than capital R, then I is equal to N Xi divided by R, which is equal to N I1, where I1 is the current due to a single cell. I1 is equal to Xi by R. Thus, if R is negligible when compared to capital R, the current supplied by the battery is N times that supplied by a single cell. Case B, if the internal resistance small r is very much greater than R, capital R, I is equal to N Xi divided by N R, which is equal to Xi divided by R. It is the current due to a single cell. This is the current due to the whole battery is the same as that due to a single cell, and hence there is no advantage in connecting several cells. Thus, series connection of cell is advantageous only when the effective internal resistance of the cell is negligibly small compared with capital R. Cells in parallel. In parallel connection, all the positive terminal of the cells are connected to one point and all the negative terminal of the negative terminal to the second point. These two forms the positive and the negative terminal of the battery. Let n cells be connected in parallel between the point A and B, and a resistance R is connected between the points A and B. Let Xi be the EMF and R the internal resistance of each cell. The equivalent internal resistance of the battery is 1 by R equivalent is equal to 1 by R plus 1 by R etc. up to 1 by R, which is n terms. We will get n by R. So, R equivalent is equal to R by n, and total resistance in the circuit is equal to R plus R by n. The total EMF is the potential difference between the points A and B, which is equal to Xi. The current in the circuit is given by I is equal to Xi divided by R by n plus R. So we get I is equal to n Xi divided by R plus n R. Next is case A. If the internal resistance R is very much greater than R, I is equal to n Xi divided by R, which is equal to n I1, where I1 is the current due to a single cell and it is equal to Xi by R, where R is negligible. Thus, the current through the external resistance due to the whole battery is n times the current due to a single cell. Case B. If the internal resistance R is very much less than R, then I is equal to epsilon by R. The above equation implies that the current due to the whole battery is the same as the due to a single cell. Hence, it is advantageous to connect cells in parallel when the external resistance is very small compared to the internal resistance of the cells. Next is Kirchhoff's rules. Ohm's law is useful only for simple circuit. For more complex circuit, Kirchhoff's rules can be used to find current and voltage. There are two generalized rules: Kirchhoff's current rule, Kirchhoff's voltage rule. Kirchhoff's first rule, current rule or junction rule. It states that the algebraic sum of the current at any junction of a circuit is 0. It is a statement of conservation of electric charge. All charges that enter a given junction in a circuit must leave that junction, since charge cannot build up or disappear at a junction. Current entering the junction is taken as positive and current leaving the junction is taken as negative. Applying the law to the junction point A that is shown in the diagram, the current whichever coming in is I1 and I2. The current which is leaving from the junction point is I3, I4 and I5. So you have I1 plus I2 minus I3 minus I4 minus I5 is equal to 0. Taking all the negative terms to the other side, you will get I1 plus I2 is equal to I3 plus I4 plus I5. So, Kirchhoff's second rule, it is also called as voltage rule or loop rule. It states that in a closed circuit, the algebraic sum of the product of the current and resistance of each part of the circuit is equal to the total EMF included in the circuit. This rule follows from the law of conservation of energy for an isolated system. The product of current and resistance is taken as positive when the direction of the current is followed. If the direction of current is opposite to the direction of the loop, then the product of the current and voltage across the resistor is negative. In the diagram, the A and the B, the EMF is considered as positive. When the proceeding from the negative to the positive terminal of the cells, it is shown in the C and the D diagram. Kirchhoff's voltage rule has to be applied only when all currents in the circuit reach a steady state condition. Here one problem we'll discuss. The following figure shows a complex network of conductors which can be divided into two closed loops like ACE and ABC. Applying Kirchhoff's voltage rule to the diagram, we'll get I1 R1 plus I2 R2 plus I3 R3 is equal to XI. And for the closed loop ABCA, I4 R4 plus I5 R5 minus I2 R2 is equal to 0. Hi students, you all have learned about the Kirchhoff's law and we will meet you in the next video. Thank you.